Establishing the identity of an aircraft pulled from the Earth requires more than finding aluminum in the dirt. It demands a documented chain of historical provenance. For the P-51B Mustang carrying the serial number 42-106602, that provenance rested on surviving records, identifiable wreckage, and serial-numbered material recovered from a French field after more than 7 decades. The recovery also defined a hard operational constraint. The artifacts could anchor the aircraft's history, but registration, identification, and authorization to fly remained separate regulatory questions. Investigators possessed the definitive legal identity of the machine, but the physical mass recovered from the impact crater lacked the structural continuity required to serve as a direct template for reconstruction. Project researchers reconstructed a record of 95 combat missions across the European theater, although several entries required interpretation where wartime records were incomplete or partly illegible. It was a high-time airframe operating under the intense operational demands of a wartime environment. Following its loss, the aircraft remained exactly where it fell, absorbed by the topsoil and agricultural cycles. This 76-year gap ended in the year 2020. A recovery team excavated the site, removing shattered aluminum, steel, and mechanical components from the soil. The recovered material was then packed for transport and later examination. By the year 2021, these crates arrived at a specialized forensic reconstruction facility in Minnesota. Upon unloading the crates, the restoration inventory began. Technicians laid out the recovered components, cleaned the material sufficiently for examination, and cataloged identifiable pieces against surviving records and factory parts information. Data plates, stamp numbers, and recognizable assemblies helped connect the wreckage to the documented history of 42-106602. However, sorting the debris also highlighted the severity of the structural problem. The forward fuselage sections were heavily compressed. The main wing box components were shattered into disconnected segments. Severe impact forces and decades in damp soil had further deteriorated the fragments, leaving the project dependent on serviceable period components and newly manufactured structure. The engineering team faced an immediate diagnostic boundary. In standard delayed forensic recoveries, an aircraft might suffer severe localized damage, yet still retain its primary geometric shapes. Bulkheads, stringers, and main wing spars usually provide a physical scaffolding. They serve as a three-dimensional guide for engineers to trace load paths and measure aerodynamic profiles. This wreckage offered no such luxury. The energy absorbed during the crash had sheared the primary attachment points and warped the surviving aluminum beyond usable tolerances. This forced a fundamental shift in the project mandate. Building a flight-capable airframe from this state required a major engineering and manufacturing effort. Because the wreckage provided no complete template, engineers combined original North American drawings with serviceable period components, wartime new-old stock assemblies, and newly fabricated parts. They had to recreate missing geometry while maintaining a clear documentary distinction between material recovered from the crash, restored period components, and newly manufactured structure. The objective was absolute accuracy, requiring the new physical components to match the exact mathematical coordinates that governed the original production line. Yet, before the team could begin synthesizing the missing structural data, they needed to understand the forces that caused such catastrophic fragmentation. With the wreckage safely in Minnesota, investigators had to determine exactly how the robust airframe was reduced to fragmented scrap. At 10,000 feet, a fighter pilot facing severe engine damage confronts a rapidly narrowing set of choices. A Mustang deprived of power can still be controlled and glided while sufficient airspeed remains, but altitude, battle damage, terrain, and hostile airspace may leave little time to decide between remaining with the aircraft and bailing out. On August 16, 1944, First Lieutenant Kenneth H. Dahlberg confronted this exact boundary. He was operating within a major engagement above the European landscape. navigating a chaotic airspace in which contemporary and later accounts place the opposing formation at more than 50 aircraft, with project research estimating approximately 80. In this high-threat combat environment, his Mustang sustained a critical projectile hit. The incoming round damaged the oil system of the Packard Merlin engine. The Merlin is liquid-cooled, but its bearings, crankshaft, cylinder assemblies, and supercharger still depend on pressurized oil for lubrication and heat control. A serious leak can drive oil pressure down, overheat lubricated surfaces, and rapidly damage bearings or other moving parts. The surviving accounts establish severe oil loss and a failing engine, but they do not preserve the exact internal sequence or the number of seconds before failure. Operating with a severely damaged engine amid a large hostile formation, Dahlberg could not rely on sustained powered flight and had little time to evaluate his remaining altitude, direction, and escape options. With the engine failing and the combat situation deteriorating, he chose to abandon the aircraft and initiated the bailout sequence. He successfully exited the failing airframe at an altitude of 10,000 feet, trading the hardware for his own survival, and safely descended via parachute into the French countryside. Relieved of human input, the aircraft descended without a pilot at the controls. Its exact attitude and flight path are not preserved in the surviving record. Trim, airspeed, battle damage, control positions, and aerodynamic stability would all have shaped the descent, but the Mustang ultimately struck the ground at high energy. When the aircraft struck the Earth, its remaining kinetic energy was absorbed through rapid deformation, fracture, and movement of wreckage into the soil. The exact failure sequence cannot be reconstructed from the public record because it would have depended on impact angle, speed, soil conditions, and the condition of the aircraft at contact. The engine, wing box, fuselage frames, skins, spars, and fasteners were all exposed to forces far beyond their normal flight loads. Aircraft structures are engineered to distribute aerodynamic loads across the wings and fuselage, not to absorb blunt force deceleration against the ground. Under such loading, the engine mass and primary structure would have contributed to widespread deformation, fracture, and separation, but the surviving record does not support a more exact sequence. The forward fuselage and the central wing box collapsed under the immense compressive forces. The structural ribs and bulkheads folded and shattered, driving deep into the soil and violently disassembling into a scattered debris field. By the time the crash sequence concluded, the force of the impact had destroyed the precise geometric relationships between the airframe components, leaving modern engineers without physical templates for reconstruction. The solution demanded a shift from physical archaeology to archival data synthesis. The engineering team located the necessary mathematical coordinates within the Ken-Jungerberg collection. The broader Ken-Jungerberg collection contained more than 50,000 original North American aviation engineering drawings spanning several aircraft programs. Within that archive, the relevant P-51 drawings preserved factory dimensions, rivet patterns, material specifications, and configuration details needed for the reconstruction. Sourcing this archive provided the foundational data, but it also introduced a severe processing constraint. Hand-drawn vellum plans exist exclusively as two-dimensional datasets, drafted in an era long before digital solid modeling. The engineering team had to convert these flat, 80-year-old paper drawings into functional, three-dimensional manufacturing tooling. This vellum blueprint translation requires strict procedural discipline. Technicians must meticulously scan and digitize the vintage drafts, handling the fragile paper with extreme care. Once digitized, engineers cross-referenced related structural drawings to reconcile dimensions, stations, assemblies, and revisions. Because aged drawing media and scanned images can distort, they relied on written dimensions and verified reference geometry rather than treating the image itself as a perfectly scaled template. The resulting values were transferred into modern design and manufacturing tools, with uncertain or conflicting details checked against adjacent drawings and surviving period components. Each line drawn on the vellum represents a critical load path that must endure dynamic flight stresses. By inputting the exact historical data into the software, the team generated highly accurate digital models of the missing airframe. These digital models subsequently directed automated fabrication equipment to cut heavy steel tooling jigs. These massive jigs act as a rigid, three-dimensional skeleton on the hangar floor. They dictate exactly where every piece of newly formed aluminum must sit to recreate the authenticated 1944 configuration. Building these steel fixtures required thousands of hours of meticulous data interpretation. A single misread dimension on the vellum could easily cascade into a major structural misalignment once the heavy metal components were mated together during final assembly. Only after the reconciled dimensions passed independent review could the team release the steel tooling for fabrication. However, locking the fuselage geometry solved only half of the structural problem. The critical lifting surfaces required an entirely different level of precision. Paper blueprints provide mathematical certainty, but how is that archival data translated into exact physical alignment for a critical aerodynamic surface? A wing station coordinate dictates the exact boundary where mathematical data meets physical reality. For the Mustang, wing station 75 required a tolerance threshold so narrow that a fraction of an inch deviation would corrupt the entire flight profile. Having translated the archival blueprints into functional tooling, the engineering team now faced the physical assembly of the main lifting surfaces. Building a standard aircraft wing allows for slight surface imperfections, but this specific airframe imposed a severe aerodynamic constraint. The Mustang utilizes a specialized laminar flow wing design. This specific airfoil is engineered to keep the boundary layer of air smooth and attached over a larger percentage of the wing surface than traditional designs. Preserving the intended low-drag profile requires close control of rib alignment, skin contour, and surface finish. Excessive waviness, steps, or roughness can trigger premature boundary layer transition, increasing drag and reducing the aerodynamic benefit the airfoil was designed to provide. Traditional string and plumb bob methods could not provide the required control. The most complex phase of this alignment involved the integration of the internal structural ribs and heavy reinforcement plates along the primary wing spar. To achieve absolute dimensional control, the engineers deployed a tripod-mounted laser measuring system on the hangar floor. They positioned the laser to project a rigid optical datum line directly through the wing structure tooling. This optical plane provided a constant, weightless straight edge that could not sag or bend over the long span of the wing. At that station, dynamic flight loads transfer heavily through the internal wing architecture, making it a major structural node. During the physical assembly phase, aviation-grade aluminum inherently flexes. Installing the heavy reinforcement plates at this location requires driving large diameter fasteners through multiple thick layers of aluminum alloy. As pneumatic rivet guns drive these heavy fasteners, the localized stress waves cause the material to shift and walk out of alignment. This phenomenon is a constant hazard in precision airframe manufacturing. Before permanent fastening in the critical area, technicians checked the relationship between the reinforcement plates, ribs, tooling, and laser datum. Where the assembly drifted from the specified position, clamps and temporary fasteners could be adjusted before riveting continued. The laser provided a repeatable reference at wing station 75, while the final aerodynamic profile still depended on the combined accuracy of the ribs, spars, skins, fixtures, fastener installation, and conventional inspection. With that geometry established, the internal configuration presented a separate challenge regarding historical exactness versus standard replacement parts. Achieving 1940s-era factory tolerances forces an immediate supply chain constraint. When restoring an early model variant, modern engineers cannot simply purchase off-the-shelf replacement parts designed for later, more common production blocks. The P-51B represents an early iteration of the airframe, built before massive standardization efforts streamlined the later D models. The team faced a constant operational trade-off. They could save thousands of fabrication hours by installing readily available, later model structural assemblies, which still met modern flight safety standards. However, choosing standardized parts would corrupt the internal forensic accuracy of the project. The commitment to absolute historical precision dictated that every internal component match the original build sheet, regardless of fabrication difficulty. This policy was severely tested at Wing Station 61.5. The structural rib assembly required at this exact coordinate was not standard. The original engineering data specified the installation of part number 97-14361. The 97 prefix is a distinct production identifier. It indicates that this specific component was actually a legacy design, originally drafted for the earlier A-36 dive bomber variant, and carried over unchanged into the early B-model production line. Later Mustangs utilized a completely redesigned rib structure at this location to accommodate different equipment loadouts and internal routing. Because the early legacy part was no longer manufactured and existing surplus stocks were exhausted decades ago, the engineering team had no external supply option. The team decided to manufacture the 97 prefix part from the original drawing. Technicians created dedicated tooling, formed an aviation-grade aluminum blank to the specified contours, and checked the completed rib against the drawing before assembly. The exact shop sequence, including any intermediate heat treatment or artificial aging, has not been publicly documented. Integrating legacy configurations like the A-36 rib into a larger assembly requires meticulous systems routing. Early production variants often featured unique hydraulic line pathways and distinct electrical harness brackets that were entirely phased out in subsequent models. By manufacturing the exact legacy rib, the technicians also forced themselves to replicate the early, more complex internal routing systems. This cascading effect means that one historically accurate structural choice dictates the entire subsystem installation surrounding it. Before final installation, quality control inspectors verified the completed rib against the original dimensional callouts. They confirmed the specified alloy and material condition against the original drawing and applicable documentation. Only after passing this rigorous verification was the part riveted into the wing box. Discrete, modern systems were incorporated only where safety required them. With the structure mathematically locked and internally accurate, only the external presentation remained to be defined. With the structure complete, the managers faced a conservation decision: protect the new aluminum while presenting the aircraft as a wartime machine, rather than a flawless modern restoration. They therefore adopted a finish policy of accuracy over perfection. The decision to apply a war-weary finish demanded forensic analysis of archival photographs to correctly map fluid stains, exhaust streaks, and field-applied paint anomalies across the external skin. To protect the newly formed aluminum, technicians used modern corrosion protection beneath the visible finish. The exact coating stack has not been publicly detailed, but its purpose was to preserve the metal while allowing the exterior to reproduce the varied sheen and texture of a wartime aircraft. Recreating a historically grounded, weathered appearance required highly controlled application techniques. The restoration was not intended to show the aircraft exactly as it appeared on August 16th, when its upper invasion stripes had already been removed. Instead, the team selected an earlier D-Day era presentation, preserving the boldly brushed black and white markings associated with the weeks after the landings. Rather than masking perfectly straight lines and applying a flawless sprayed finish, technicians painted the stripes by hand, reproducing the uneven edges and visible brushwork documented in the chosen scheme. Furthermore, an operational liquid-cooled engine produces a distinct signature of exhaust soot and fluid leaks. Painters utilize specialized airbrushing and localized chemical weathering to simulate heavy carbon buildup along the fuselage flanks behind the exhaust stacks. They meticulously mapped oil streaks along the lower engine cowls, ensuring the simulated fluid paths matched the aerodynamic airflow patterns that would naturally pull leaking lubricants backward during high-speed flight. Once the final chemical clear coat sealed the weathered finish, the restoration process concluded, transferring the project from the hangar floor back into an active flight environment. In July 2026, the completed Mustang advanced to the runway and made its first post-restoration flight. Before departure, the crew carried out the checks and engine runs required for the first flight. Warren Peach then took the Mustang into the air for a cautious post-restoration evaluation. Public reporting confirms a successful flight, but the detailed test card, load schedule, and engineering measurements have not been released. Upon landing, post-flight inspections verified that no fluid leaks occurred outside of the simulated weathering boundaries. The airframe was subjected to a thorough mechanical audit, ensuring the thousands of internal fasteners held their torque specifications after experiencing real-world flight stresses. The flight demonstrated that the aircraft was operating under the authorization and limitations applicable to its airworthiness status. But the public record does not establish that every regulatory or flight test phase had been completed. Its continuing operation remains subject to modern inspection and maintenance.